We're going to talk about basically matter. We're going to talk about different states of matter. We're going to talk about physical changes, chemical changes. We will also talk about mixtures and all that good stuff. So let us get into it. So when we talk about matter, matter is really anything that basically occupies space and has mass. And really, when we talk about matter, a lot of times we do focus on really the different states of matter. There is the solid state. And in the solid state, everybody is pretty tight to one another. They're packed in there pretty good. We also have the liquid state, where they're still relatively packed in pretty close to one another, but there's a little bit more room for movement. They're able to sort of pass one another. That's why when we think about liquids, right, they are fluid. We can pour them and stuff like that. You can't really pour necessarily a solid. It all just falls as one. In the last sort of state of matter, we have gas. And in the gas state of matter, pretty much everybody has broken apart from one another. They're flying around. They're causing collisions with the container, and that causes pressure as they kind of hit the containers. So a lot of what we look at in chemistry is sort of these different states, how they change from one state to the next. A reminder that a couple changes of state, when we go from solid to liquid, that is the process of melting, right? Like if you took an ice cube out, it would start to melt. As we go from liquid to solid, that's the process of freezing. Yeah. If we go from liquid to gas, that's the process of evaporation or vaporization. Going from gas back to liquid, that is the process of condensation. As we go from solid, skipping the liquid part and ending there at the gas part, that is what is known as sublimation. And lastly, as we go from the gas part, once again, skipping the liquid part and ending up there in the solid spot, that is what is known as deposition, like you're depositing something on it. Now, when we talk about these processes of melting or freezing, does melting and freezing occur at different temperatures or the same temperatures? If the melting and freezing occurs at the same temperature, actually. So these things do occur at the same temperature. It's what is sometimes referred to as the normal melting point or freezing point. So melting point or freezing point there of a substance. So for example, water at exactly 0 degrees Celsius, that is where it both freezes and also melts. So exactly at 0 degrees Celsius for something like liquid water or water, thank you. You basically have both phases happening at the same time. So you got like ice crystals. So you got some solid, you got some liquid occurring at say 0 degrees Celsius. It's not until you get a little bit above 0 degrees Celsius that you really do get sort of liquid. It's not until you get a little bit below 0 degrees Celsius that you actually have solid. But right there, exactly at that 0 degrees for water at the melting point and freezing point, you basically got both phases sort of happening. Same thing happens here, the process of evaporation and condensation. It also occurs at the same temp. That is what is sometimes referred to as the normal boiling point of a substance. Boiling point. And once again, that does happen at the same temperature. So for example, using water again, that's 100 degrees Celsius where that occurs for water. So exactly 100 degrees Celsius, You have basically some liquid water. You also have some steam or gas coming up, which is water vapor coming off of it. So it basically happens at the exact same temperature. It's not until you get a little bit again above that 100 degrees Celsius that you really do transition fully into the gas phase. Not until you're a little bit below that 100 degrees that you're again back in the liquid phase. Any questions on that there? Now, we also will talk about in the next chapter we discuss as well, but there is energy associated with doing these processes. So as I go from solid to liquid to gas, do I need to put energy in to do that or take energy out to do that? So if you go from solid to liquid to gas, you need to, if you take an ice cube out, what happens to it? It starts to melt because it is gaining energy, right? So you take liquid water, you want to make pasta, you put fire underneath it, right? It starts to boil, right? You create gas basically. So that all requires energy to be put in, or energy to be absorbed. And as we'll talk about more in the next chapter, that is what is referred to as a endothermic process. And it is opposite as you head the other way. If you go from gas back to liquid, back to solid, we have to really release energy in these cases. So if you think about gas molecules, which are flying around, if they lose energy, they're not flying around as fast. And when they actually come in contact with other gas molecules, they no longer have enough energy to completely escape each other. So they kind of clump and drop into the liquid phase. If you continue to remove energy at that point, they will continue to kind of come together because they really can't start passing each other or anything like that. And they'll go into the solid stage. So as we do those processes in that order, energy is released. And that is what is referred to as a exothermic process. Any questions on any of that there? Go that way. So as I mentioned, matter is basically the stuff that the universe is composed of. It does pretty much have mass. It occupies space, and obviously that's pretty much everything or most things. So as we just talked about, there are the three states of matter, which is important. Solid, things like wood, bone, steel. Solid things have a definite shape, and they are difficult to change, or sometimes referred to as being rigid. Clearly, this tabletop is a solid. It's not that easy. I can't just fold it over, right, and change the shape of it or anything like that. So it's very difficult to do. Liquids like water, gas, do not have a definite shape, but they do have a definite volume, and they will take the shape of whatever container you put it in. So what that means is, obviously, if I had 10 milliliters of water and I had it in a cup, it would take the shape of the cup. If I took it, threw it in the trash can over there, it would take the shape of the trash can. If it was in one of those silly straws, right, it would fill up the silly straws the way the shape is. What it means is that it has a definite volume is if you started with 10 milliliters of water and you like moved it from one container to the next and you're not a klutz and spilled it anywhere, you should still have 10 milliliters of water all the way through as you transfer from one spot to the next. Gas, on the other hand, things like air or gas, they take the shape of the container and they fill it uniformly. So the idea with gas is they are flying around, so they are completely filling the actual container uniformly as they're moving around. That's something we'll talk about when we get to the gas chapter. That's something that deals with ideal gas. Is one of the ideas of ideal gas is, really the volume of the gas is the same as the container because it's flying around and really filling the entire container uniformly. So here's obviously some liquid in different containers and obviously taking the shape of it. Here's the three states of water. Again, that is ice, liquid water, and gas or steam. And as we might have talked about before, water is an unusual substance, as the solid version here, as we talked about, is actually less dense, right, than the liquid version. And you can see that in this picture as the water molecules come together and they really bond with each other. It creates all these open areas in the water molecules. And again, if you think about, as we talked about with density, which is mass over volume, that's going to increase the volume and thus will decrease the density of solid water versus obviously liquid water, where you can see they actually get, because they have enough energy, a little bit closer to one another. They're able to move around. So it's a very unusual sort of characteristic. As we talked about, most things are actually more dense in their solid state than in their liquid state. So water is a little exception of that. But as they lose energy and they start hydrogen bonding, which is what they're doing here, they kind of keep a pretty good distance from one another. And that creates all that open sort of space between them. Any questions on that? And obviously in steam, when we start to boil and we see the steam coming off, that is our water molecules that are bouncing around, obviously, and creating pressure. Now, the state of the given matter does depend on really the forces that hold it together. So we'll talk about this in a later chapter, but the idea here is there are some forces which are referred to as intermolecular force. And that's basically the force that holds two molecules together. So for example, if you had a water molecule like we were looking at, it is the force between those two water molecules that basically hold it together. So that's what kind of keeps them there. For example, for water, if these were two water molecules, that would be what is known as hydrogen bonding, which is the force that holds it together. And hydrogen bonding is a relatively strong intermolecular force. So the stronger the intermolecular force, the most likely it will not be a gas in normal conditions. The weaker the sort of force that holds the molecules together, the more obviously it will be a gas in certain cases. For example, if we took something like methane, which is CH4, basically the stuff that comes out of your gas vent there in lab, right? When you light your Bunsen burner, clearly it's a gas. Methane is a nonpolar molecule and basically held together by a very, very weak intermolecular force. So the methane molecules together are held very, very weakly, which means it just takes not very much energy or stuff for it to just behave in the gas phase. The other thing that those forces will affect are things like boiling point temperatures, melting point temperatures. The weaker the intermolecular force, the lower the melting point and boiling point, the stronger the intermolecular force, the forces that hold the molecules together, the higher boiling points and melting points that you would expect to see. So things that are solid, as we talked about there, are rigid. They have that fixed shape. Our liquids have that definite volume, but takes the shape of the container. And again, gas have really no volume and no shape, but takes the shape and volume basically of its container. Any question on the different states of matter? So let's talk a little bit about physical properties and physical changes, and also chemical properties and chemical changes. So when we talk about a physical change, that is something that can be measured without really changing the composition or identity of a substance. Typical physical properties are things like odor, color, volume. Probably the most common sort of physical property we come across a lot in chemistry is the state, as we were just talking about. You know, is it solid? Is it liquid? Is it a gas? Things like density, melting points, and boiling points, those are all physical properties. Physical properties usually go with physical changes. And when we have a physical change, basically what we start with and what we end with are fundamentally the same thing. So when something goes through a physical change, really some type of physical aspect of it changes, but fundamentally what it is still the same thing. So for example, when we take our ice cube out and we let it melt or we heat it up or whatever it may be, when the ice cube melts, it becomes liquid water. And then if we took that water and we started to heat it up and boil it, it would go from liquid water to steam. All three of those things, the ice cube, the liquid water, and the steam, they're all H2O. Yeah. They're all water fundamentally. It has not changed to anything different. So when you do any of those processes, that is a physical change. And one of the important things about a physical change is, typically speaking, you usually could sort of kind of put back the original thing in a physical sort of method. But the main thing is, it is really what you started with is what you end with, may just look different. If you had a peanut or something like that, and you crushed it, they still are fundamentally peanuts. They just look very much smaller, right? And stuff like that. So those are all examples of physical changes. You know, if you had a piece of paper and you colored it red, it is still fundamentally still a piece of paper. It just looks red. So those are all physical type changes. And again, very common physical properties is what you see there: solid, liquid, gas, odor, color, melting points, and boiling points. Any questions on that there? So as I mentioned before, our block of ice, again, we could record the temperature where it starts to melt, and that would be a physical property. And again, the physical change there. If you wanted to, you could capture the steam, cool it back down, get the liquid water, take that liquid water, put it back into the freezer, and you would get back your ice. So again, it is fundamentally the same thing. There really is no chemical reaction that has taken place. It's just a physical sort of change that occurs. Now, that is different than a chemical property or a chemical change. When we talk about chemical properties are really the resistance or ability of something to go through a chemical reaction. So for example, a lot of chemical changes are what are referred to as chemical reactions, but in a chemical change, the important thing here is what we start with and what we end with are two fundamentally different things. So what we start with and what we end with are two fundamentally different things. The other important part of that is you cannot get back the original sort of substances by any type of physical means. So you can't freeze it, you can't boil it, you know, filter it and get back the original substances. So for example, when we take, say, hydrogen gas plus some oxygen gas and we get some water that is formed, again, you could do whatever you like with the water. You could boil it, you could freeze it, you can melt it if it's solid, but you will not get the hydrogen gas and oxygen gas back. Otherwise, when we would put water up on the stove to make pasta, there probably would be an explosion because you would have hydrogen gas and oxygen gas happening. So that doesn't happen. It has fundamentally changed to something different than what it started with, and we can't get back, you know, what it our original guys through any type of physical means. So physical changes, what we start with and what we end with, basically the exact same thing fundamentally. Chemical change, what we start with and what we end with are two fundamentally different things. And you can't really get back the original guys without going through another chemical reaction. So in order to get these guys back, we would actually have to do another chemical reaction where we would run an electrical current through it. And you could break apart the water into hydrogen gas and oxygen gas. We'll do it a little bit later on in a lab, I think. So you could actually see that. But you can't really get back the original components by any type of physical means. You have to do a chemical reaction. So chemical change is a chemical reaction. Evidences of chemical reactions. When you look at them, you see bubbles maybe form if you do something. Maybe a solid forms. Maybe there's heat and stuff coming off. These are examples of things that you could kind of recognize a chemical change happening. So as I mentioned there, the hydrogen gas burning and oxygen gas to form water. Once again, once you form that water, it's not going to really go back to hydrogen gas, oxygen gas without another chemical change. When we form something like rust, rust is basically iron and oxygen coming together. And when it comes together, it forms iron 3 oxide, which is rust. But basically at that point, the iron and the oxygen are now sort of bound together. And if you ever study something that's rusted, you can't kind of get back the iron by itself or the oxygen gas by itself by just trying to clean it, filter it, heat it. So it has really went through a chemical reaction here and changed. And again, that would be an example of a chemical change as well. Any questions on the difference between physical change, chemical change? And another example there, hard-boiled egg. Obviously, as you're cooking it, inside is going through some changes in their physical appearance and also the chemical appearance. And then clearly when we eat things, right, our enzymes and stuff take care of a lot of those things, break it down into other things that go through chemical reactions, and we can't get it back. So again, a summary of chemical and physical changes. Physical changes one or more of the physical properties, but no fundamental component is changed. Very commonly, it is those changes of state that we see are very common physical changes. Chemical does involve some type of fundamental change where a chemical reaction has occurred, and what you start with and what you end with are really two fundamentally different things. Silver tarnishing by the reaction. When you have anything that sort of oxidizes, right, and goes through oxidation, like metals or something like that you might have, that really is sort of a chemical reaction that's occurring. It's basically the oxygen and the metal coming together, and there's a change that really does occur in those cases. So let's talk a little bit about elements and compounds here. An element is a substance that cannot be separated into simpler substances by chemical means. So you could think of elements as sort of your like alphabet, if you will. It's kind of as far back as you could go. And different combinations of the elements give us different molecules or compounds. Elements are as far back as you could go. You can see them on the periodic table. There is where we have all of our elements listed. The simplest representation of an element is an atom, as we'll talk about in another chapter, but basically has protons, protons, electrons, and neutrons, right? We'll talk about. So basically every element's representation is an atom, which has those different parts. Now, some atoms or elements are made up of what are referred to as molecules. So some elements come naturally as basically two of them together. So things like hydrogen, nitrogen, oxygen, fluorine, chlorine, bromine, iodine. These guys come as what are referred to as diatomic molecules. That is naturally how they come when they are by themselves and not combined with anything else. So something like hydrogen is basically two hydrogen atoms bonded together. Something like oxygen is two oxygen atoms bonded together. That is naturally how they come. Those are still elements, and they're also molecules because there's more than one atom together, basically, that is there. So each element is made up of a certain kind of atom. If you have a pure element, say of aluminum, it will only have aluminum atoms in it. And as I mentioned there, we do have those guys that you should know. That is naturally how they come as elements. So let's talk a little bit about a couple of things. When we do look at the periodic table, we'll officially talk about it, I think, in a later chapter. But basically, if you look at the periodic table, somewhere around boron, you usually will see like a staircase that sort of comes down. And really to the left and on the bottom couple rows there as well, these guys, these are what are referred to as metals. And these are elements that are considered metals. Metals are good conductors of heat and electricity. They are usually shiny. They usually can be pulled into wires and things of that nature. So those are metals. If you go to where that staircase is and kind of go to the upper part of it, those guys are what are referred to as non-metals. And those are basically opposite of metals. Those are bad conductors of heat and electricity. They're usually dull and brittle. And actually, kind of on that staircase, as we'll talk about it when we get there, these are what are referred to as metalloids. And they're sometimes called semi-metals. And basically, you can kind of see its location. Metalloids basically will have properties that fall both like metals and properties that fall like non-metals. There's sort of that transition as you go from metals to non-metals on the periodic table. So these guys in the metalloid region will have properties similar to metals and properties similar to non-metals, where they're sometimes referred to as semiconductors in that sort of range, because they have properties that are very similar to metals and some that, again, are very similar to non-metals. So most elements will fall into one of those three sort of categories. And again, metals are also basically these guys down here. Either metals, non-metals, or metalloids. And again, metals being good conductors of electricity, shiny, and non-metals basically being the opposite there. Any questions on that there? And we'll talk more about the periodic table in a later chapter, I think. Now, earlier we talked about elements from the periodic table. Those are things that, for the most part, come as what are referred to as being monoatomic. So most of the guys on the periodic table are what are referred to as being monoatomic. And that basically just means they come as one atom, basically, is how they naturally come. Again, those ones that I listed on the previous slide come as diatomic molecules. They come as twos. By the way, nothing on the periodic table has a charge when it is by itself. Yeah, so things only gain charges when they start combining, as we will talk about also in a later chapter. So sometimes people think they all have charges. They don't. So if you have a piece of just copper metal, does not have a charge. So what is the definition of a molecule? So a molecule is really just the combination of two or more atoms. So to classify something as a molecule is a combination of two or more atoms. They could be the same element, they could be different elements, and those are both would be classified as molecules. So for example, H2, this is a molecule. It is also an element because it is only made up of hydrogen, so the two hydrogens together. H2O is a molecule. It is not an element. So not an element because it has hydrogen and oxygen together. So in order for it to be an element, it can only be that one thing, not an element. This is, as we'll talk about here on the next slide, it is a compound. And a compound is when you have two or more atoms of different elements together. So that is the major difference. You got to have two or more atoms of different elements for it to be a compound. But for it to be a molecule, you simply just need 2 or more atoms together. So it doesn't matter if they're the same, doesn't matter if they're different. So both of those are examples of molecules, but only the guy on the right is actually a compound. The guy on the left is an element. And the guy on the left would not be a compound either, because obviously it has just one element involved. So sometimes people get confused, molecules, compounds, and stuff like that. Any questions on that? So that is what this definition says. A compound is a substance composed of atoms of 2 or more elements that are chemically united through some type of bonding. So for example, water, as we just saw, pretty much has 2 hydrogen atoms together with 1 oxygen atom, and they're held together by sharing of electrons, like so. And again, as we just saw, that would be both a molecule and a compound. Now, compounds you can break back apart into elements. So you can take a compound like water and you can, as we just talked about, run like an electric current over it. And it would break apart into hydrogen gas and oxygen gas, which these are both elements. And they are both actually diatomic molecules as well. But that is as far back as you could go. You can't take the hydrogen gas and oxygen gas and continue to do something to it to break it down any further. That is as far back as you go. So as I mentioned earlier, we could think about sort of the elements like the alphabet. I think there's only still 26 letters, I think. And we have dictionary full of different words. You know, dictionary used to be a book. You look up things and what things mean instead of Googling it. But, you know, Google has the thousands and thousands of words on it when you Google it. But we can make different combinations. Same thing with the elements, different combinations, different amounts of each of these elements gives us different compounds. And usually the compounds are very different than the elements that make them up. You know, for example, sodium is a metal. Chlorine naturally comes as a toxic green gas, but through the miracle of chemistry, when it comes together as sodium chloride, it's like salt, and we put it on our fries and we're okay. But you would not want to eat, obviously, the sodium metal by itself or the chlorine gas by itself either. You wouldn't get too far, I don't think. But again, very, very different properties than the elements that make it up. Carbon dioxide, which is CO2. That is a combination of carbon and oxygen, which would make it a compound and also a molecule. Again, would not be an element in this case. Obviously, hydrogen gas and oxygen gas, very different properties like explosiveness and that type of stuff compared to just water, right, which is pretty non-toxic and stuff like that. So very, very different properties of those elements that make up compounds than the compound itself. Any questions on any of that? So the next thing we're going to talk about is mixtures and pure substances. A pure substance is a form of matter that basically is composed of just basically one thing. So a pure substance, for example, could just be water. And that would be a pure substance. That's the only thing I got. We could also have sodium chloride or salt, which would be also a pure substance. Now, when we take 2 or more pure substances together and mix them, we get basically what is known as a mixture. And a mixture is really the combination of 2 or more pure substances. The important part about it is they retain their identity. So although they are mixed together, they are still retaining their identity. All the parts of the mixture are not really changing to anything different. So would that be a physical or a chemical change if you make a mixture? It is a physical change. So if you think about what we did on Monday, you took some water, you took some salt, the salt dissolved in the water, you had some sand in there. That was all a mixture. You filtered out the sand, so it was still the sand. You heated off the water, which lets the water evaporate. You could have grabbed it if you wanted to, but what you were left with in your evaporating dish, if you got to that part, is just the salt left, right? So although they are mixed together, although they may look like something has reacted, it is not a chemical reaction. It's really a physical change that occurs with a mixture. Any questions on that there? Now, there are two different types of mixtures like we talked about, I think, on Monday during lab. The first type is a homogeneous mixture. And in a homogeneous mixture, with sufficient mixing, everything will pretty much dissolve, mix together. It is basically said to look the same throughout. So if you just think about maybe the salt and water part of it, that is a homogeneous mixture. When you mix the salt and water, it's going to dissolve. When you look at it, it looks just like water, right? If you ever swallowed ocean water, right? It looks like water, but it kind of tastes salty, right? So, it just looks like water. You can't see it. And that is a homogeneous mixture. Same thing if you took sugar and put it in water. If you took some sugar, it would dissolve, obviously. And if you just looked at it, it just looks like water. You can't really see the sugar. So although the sugar and the salt in those examples are not, you're not able to visually see it, they are still there. There was no reaction. It didn't really change into anything else. The other type of mixture is a heterogeneous mixture. And in a heterogeneous mixture, even with sufficient mixing, you still see different phases, you still see different layers. So if you go back to your sand in your water, you can mix that all day. The sand is never, ever going to dissolve, right? So you will still be able to see the sand in it. If you took some sand and like metal pieces and mixed it, you would still see the metal pieces in it. If you made some chocolate chip cookies correctly, you see the chocolate chips, right? It's still in there. And it's a mixture of a bunch of stuff together. So heterogeneous, even with sufficient mixing, you're still going to see the different layers. So regardless, though, of whether it is a homogeneous mixture or a heterogeneous mixture, they do retain their identity, and you can separate them out through physical means to get back the original components. So much like we did on Monday, you were able to do some physical processes to separate out those mixtures to get back the original components. So let's take a look. So one of the things that we did the other day, filtration, right? And in filtration, it's a good way to separate out, as you probably saw, a solid from a liquid. So it's a good way to separate a solid from a liquid. And you could use something like, obviously, like you did there, a funnel that has perhaps a piece of filter paper. And much like you did, you probably have something underneath that would be good. If you took your sand and water mixture, by the way, sand and water would be a heterogeneous, right? And you poured it in there, the liquid part would go through, and obviously the sand would get caught up there on the filter paper. So just by this very simple process of just basically using filter paper and funneling it or filtering it out, you're able to get back the sand. You could take the filter paper, let the sand dry out, right? And it'll be just like it was originally. Obviously, the liquid that goes through, if this was just water, would be just like the water that you had before. So by physical means here with this heterogeneous mixture, we're able to separate out both of the components of the mixture, just like they were at the beginning. Here again, nothing has fundamentally changed, which is why this is a physical change that is occurring in this case. Now, if you took something like our salt water, and our salt water is a homogeneous mixture. You could do a process if you really wanted to sort of collect everything. You could set up a process here where you have a closed situation, maybe 2 flasks, and you have this tube that connects it and you keep the tube really cold. And you put your salt water here on one side. And if we then decide, well, I'm going to heat this. As I start to heat salt water, the water part's going to start to do what? It's going to start to, when you heat liquid water, it starts to evaporate, right? So as it starts to evaporate, it's going to create steam, right? And if it's in this container here with nowhere to go, steam's going to go this way. What happens when we have steam and we then cool it down? It goes through condensation, right? Gas back to liquid, and out on this side would drop our red water. We would continue to heat this until pretty much all the water evaporates, and the only thing we would be left with on the left-hand side here is our salt. We'll make it red salt, so you can see it, but we'll end up with just the red salt in that way. And this process, which is known as distillation, is a way that we could keep, obviously, or get back both parts of the mixture. In this case, we didn't let the water just go off into the environment, right? We were able to trap it and get it back. What you guys did on Monday, and he'll do today as well, you put it in an evaporating dish, and obviously as you heated it, the water was just lost to obviously the environment, and you were left with just the salt in the evaporating dish. But if you wanted to collect the water, you absolutely could cool it back down, and you would get the liquid water back. So on the right there is distillation, and on the left is filtration. 2 physical processes that allow you to separate out any mixture, be it homogeneous or heterogeneous. Any questions? Yeah. Decanting, and basically is kind of the same idea as filtration without a filter. You basically decant means you just pour off the liquid part. And solid. A lot of times you do something like decanting after you centrifuge it, right? So when you centrifuge a, say, test tube, if you have like a mixture of solid and liquid, what happens is like the solid gets all compiled there on the bottom, and you have the liquid part. And a lot of times the process of decanting, you just pour off the liquid part, leave the solid behind. And again, that's a physical way of separating out things. Yeah. Other questions? So why is it not a chemical change? Why does it look like perhaps the salt is gone and it went away and it reacted? It's really because we can't visually see it anymore. So when you take something like sodium chloride, it's really an ionic compound. It's really sodium ions and chloride ions together. And basically in its solid form, it is kind of packed in there pretty much tight together, all those ions. And then a really important thing in chemistry is the idea of opposites attract. So things that are positive, negative are attracted to each other. Things that have the same charge, things that are negative and negative, they don't want to be near each other. They repel each other. Things that are positive and positive do not want to be near each other either. So really that positive negative attraction is something that brings things together. So negative, negative, positive, positive, they repel each other. So when we take something like water, water actually has charges, and we'll talk about it. It's what's referred to as being a polar molecule. The oxygen side of water is more negative. The hydrogen side is more positive. So what happens when we dissolve something like salt in water, the water molecules basically go in, pluck off some of these ions. And what happens is the sodium ion gets surrounded by the negative side of water, which is the oxygen. And what happens to the chloride part, which is the negatively charged guy, it gets attracted to the positive side of water. So the hydrogens are more attracted to it. And that is what keeps that really strong attractive force of the sodium ion and the chloride ion apart from each other, basically, right? They get surrounded by a bunch of water molecules. That also makes it visually, we can't see it anymore. It's like gone. It's all trapped in the matrix. We could again re-see it like you saw, because when we start heating this, the water will start to evaporate, right? and these guys will eventually all evaporate. And then what happens is these two guys have nobody in their way. They're going to come back together to make sodium chloride, and your solid reappears. So that's why it kind of looks like it goes away. And then when you heat it, the water molecules escape. And now there's nothing to prevent those really strong attraction, be the positive guy, negative guy, to come back together. And that's when the solid basically reappears. Any questions on that? By the way, when we do dissolve something, we oftentimes do what? Stir it, right? Adding energy, right? Also throwing a bunch of water molecules all over this. So a bunch of them get guys. And that's how they're able to kind of pry them apart and surround them. We have that energy that's needed by stirring, and also putting a lot more water all over the place that allows those guys to be plucked off. Any questions on that? So as we talked about, those are two ways to separate out a mixture. What I bad drawing on the right there was distillation, and filtration, obviously, we used there before. So distillation is a really good way to separate out a homogeneous mixture where you can't really see the different components. We're basically using, in the process of distillation, we're using the differences in melting points and boiling points, basically, really boiling points. So here we basically have two things. We have water, and we have the ionic compound or the salt. And earlier we were talking about that the strength of the forces that hold a molecule together results in either a lower boiling point or higher boiling point. In comparison, water has actually a much lower boiling point than the ionic compound. The ionic compound is held together very strongly. Most ionic compounds will never boil. That's how strong they're held together. You could heat the heck out of it. It will not boil. So because water actually boils first, we're able to boil the water and basically get the water away from the ionic compound. And that again allows the ionic compound to come back together. So the process of distillation is using really some differences in physical properties like boiling points to allow you to separate out the mixture. And clearly this picture looks exactly like my award-winning art that I drew earlier, but that's probably a prettier picture, I suppose, of distillation. Question on mixtures, way to separate out mixtures, compounds, elements, states. All right, that is chapter 3. Yes. All right, we're going to then roll actually to chapter 10. Okay, so we did 3. We're now skipping upwards to 10, and then we'll come back to some of those chapters. So chapter 10 has to do with energy. So we're going to talk a little bit more about energy in this chapter. We touched a little bit upon it just a second ago about endothermic and exothermic reactions. So we'll talk more about that. We'll talk about ways to represent energy, and we'll also talk about specific heat in this chapter. So when we talk about sort of energy, there's a couple of things that's important to understand. One is the conservation of energy, which is, if I hold on to that there, our conservation of energy. So energy is neither created or destroyed, but it can be transferred. So one really important sort of idea of how we think about energy is there's sort of a perfect transfer of energy from one place to the next. And there's basically two things that we oftentimes look at. One is the system. So the system is the part of the universe that we are interested in. For us, the system could be your test tube, it could be your beaker, it could be whatever you're working with. That is the part of the system that you are actually interested in. Everything else outside of that system is considered the surroundings. So a lot of times what we talk about is, the idea of system and surroundings. And we talk about energy going from the system to the surroundings or from the surroundings to the system. And the idea here is whatever amount of energy that one loses is the exact same amount of energy that one gains. So we talked about exothermic and endothermic. For one of the things, either the system or the surrounding, it will be an exothermic process where it releases that energy. And for the other, it would then be an endothermic process where it gains that energy. And the amount, again, of energy that it loses or gains will be the same. We will see here, we just sort of denote the difference by the sign of the value. So either it'll be negative or positive, depending on whether it's an endothermic or exothermic process. There's three types of systems that we oftentimes deal with. An open system, you can exchange mass and energy with the surroundings. A closed system, you could transfer energy, but not mass. And an isolated system, really no transfer of mass or energy. For the most part, most of the time in our labs and stuff like that, it's more of an open system. You know, we could transfer mass, we can put stuff in and out of the test tube. You know, if we hold the test tube, maybe it gets hot, maybe it gets cold. So there's that transfer of energy that's basically occurring. We do use a closed system sometimes, but not so much isolated in a lot of cases. And here's the example again here in that open system. We could take stuff in and out. So that's the mass. We could also have the transfer of heat. In the closed system, put a stopper or something on it. We're not going to lose any mass or anything like that, but we will have that transfer of heat. And an isolated system, pretty much nobody's transferring from the outside to the inside in terms of heat or mass. And that's an isolated system. So energy is really the capacity to do work. And work can be either done on somebody or work can be done by something. Since energy is the mass is measured as work, work is force times distance. There are different types of energy that we could come across. There's chemical energy, and that's the energy that's stored within a structural unit. For example, like bonds, when we make or break bonds. So when we make a bond, do we have to put energy in to make a bond or take energy out to make a bond? What do you think? When we make a bond, it actually is energy being released, right? So we got these things that are moving around with a lot of energy. As they lose energy, they kind of slow down and allow them to come together to make the bond. So energy is released in this process when we make a bond. And as we talked about earlier, that is what is referred to as being exothermic. When we break a bond away, it is actually a process where you have to put energy in. So you have this bond and they're happy together. When you put energy in, they all gain energy. They start wiggling away from each other and they're able to break apart the bond. And when we break a bond, it is actually going to have energy absorbed, which is an endothermic process. Also, some chemical reactions will either release some excess energy to the surroundings. Some chemical reactions will absorb energy overall as the process occurs. There's potential energy, which is the stored energy or the energy of an object based on its position. That is the classic example in most books of like the giant boulder at the top of a cliff, right? That's about to fall off. So based on its sort of location, it has a certain amount of energy that's associated with it. When it actually does fall off the cliff and it starts moving, that is now kinetic energy, and that's the energy of motion. So our potential energy transfers to kinetic energy. And what happens, right? Hopefully there's nobody standing there. And it hits the ground. It transfers energy to the ground, right? Or the person that's standing there, right? It transfers it as it bangs on them. So it transfers that energy, and it also ends up with less probably potential energy at that point because it's now at a lower spot. But once again, it did not lose any energy in that process. It was transferred. So our potential energy transferred kinetic energy. When it hit again, it transferred to the cement, some of that energy. So again, there's this idea of log conservation of energy where we do have sort of a, if you want to think of a kind of a perfect transfer of energy from one thing to the next. Any questions on that there? Now, there's also thermal energy. Thermal energy is the energy due to motion. So thermal energy. And that's the energy due to the motion of molecules. So thermal energy is responsible for the area of the motion of molecules. The more molecules you have, the more thermal energy that you actually have. Now, temperature is a relationship to energy, but temperature and thermal energy is different. Temperature is sort of representative of sort of the energy that's occurring or energy change that's occurring, but thermal energy is different. So, for example, if you had a bathtub full of water, say at 35 degrees Celsius or something like that, and you had like a coffee cup at 90 degrees, the coffee cup actually has less thermal energy than the bathtub. Bathtub has a lot more molecules, a lot more random motion. So a lot more thermal energy than the coffee cup, even though the coffee cup has a higher temperature. The reason a coffee cup has a higher temperature is there's less molecules in a very smaller area, right? So the energy that it's going to give is going to have a greater energy change than trying to heat up a giant thing of water, right? And a big bathtub is going to take a lot more energy to raise the temperature of it. So again, temperature and thermal energy are different. Thermal energy related to how many molecules or atoms or particles there are, the more thermal energy. And the temperature, again, just sort of a measure of that change of energy that occurs. When we talk about thermodynamics, which is really sort of what we're talking about here, the actual first law of thermodynamics is what we just talked about there, the conservation of energy. So that is the first law of thermodynamics. Thermodynamics really is the study of heat and other kinds of energy and their interconversion. And when you take 1B, you'll learn more about other parts of thermodynamics. And also 1A, you'll learn more about energy. But thermodynamics oftentimes deal with overall the idea of whether or not a reaction is spontaneous or not. And one good thing to keep in mind as you go through your chemistry career, the idea of spontaneous. Sometimes when we say, hey, this reaction is spontaneous, we associate, oh, that must mean it happens really fast. And that's really not what spontaneous means in the context of a chemical reaction. If we say something is spontaneous, really what that means is thermodynamically speaking, under those conditions, this reaction should occur. It may occur really fast, it may occur really slow, but the conditions are okay for that reaction to actually take place. When you deal with how fast or slow a reaction takes place, that's actually chemical kinetics, which I think you guys do in 1B as well. So that's when you deal with how fast or slow. But when somebody says, hey, this reaction is spontaneous, sometimes people have an idea like, oh, you snap your finger and it happens really, really fast. But that's not the case. Again, it just means that this reaction should take place under those conditions. There are certain functions which are referred to as state functions. State functions are properties that determine the state of a system, regardless of how it is achieved. The idea of a state function is this: it doesn't matter how you got there. Really, the only two things that matter is basically where you started and where you finished. So those are really the only two things that are really important when you're dealing with the state function. State function could be energy, pressure, volume, or temperature. For example, if we look at these hikers, they both started here. The blue hiker took the direct route up the hill. The red one took the scenic route around the hill. But at the end, they both ended up basically in the same location. So in terms of their potential energy, they're both basically standing in the exact same spot, which means they both basically have the exact same potential energy based on where they started. So that is the state function. Excuse me. That is also why a lot of things when we do like the change in something, it is final minus initial state. So if you look here, change in energy, final minus initial, change in pressure, final minus initial, change in volume, final minus initial, change in temperature, final minus initial. It doesn't matter if it takes 9,000 steps to get there or 2 steps. The really important thing a lot of times with energy and those type of things is really where you started and where you ended. As we'll talk about in this chapter as well, not all reactions happen like in a one-step process where it goes from starting material to ending material. There may be several individual reactions along the way. And again, the only important thing is where you started and where you ended. When we talk about a chemical reaction, there are 2 parts to it. There are the reactants, and they go to the products. And really the reactants are your starting material, and the products are really your ending material, if you will, or the stuff that is formed. So a lot of times, as we will see in this chapter, one very common way that we calculate the change in energy is to add up all the energy of the products minus all the energy of the reactants. So all the energy of the products would be your final state. All the energy of your reactants would be your initial state. So you're essentially taking final minus initial. So really here, this is sort of our final, and this is our initial when we talk about a chemical reaction. Reactants, what we start with, they were initially there. Products, what is formed. Any questions on that there? So a couple important units of energy that we do come across a lot, and we do want to make sure that we know. Most often, a joule is used as the unit of energy. Also, a kilojoule is a very common unit of energy. That's 1,000 joules. So that's the kilo conversion. We also use calories, which is actually lowercase c. We also will use kilocalories. Those are 2 common sort of units. A calorie and a kilocalorie, again, 1,000 calories and a kilocalorie. The relationship of a joule is, this does pop up occasionally, kilograms, meters squared, seconds squared. So that does sort of pop up occasionally. By the way, none of these are negative. That's just PowerPoint, obviously. This is a really good conversion as well. 1 calorie is 4.184 joules. So you should know that. That is something that does pop up a lot. Now, when I talk about calories, although we don't use it all that much, too much in this class, but it does come up a lot in some other classes. That is different than a nutritional calorie, which is actually a capital C. I'll draw it like that. So a nutritional calorie is actually 1,000 of the little calories are a kilocalorie. So a nutritional calorie with a capital C is actually 1,000 of the little guys. So when you're talking about food and stuff like that, or, you know, like your nutritional label on the back of food, and they talk about calories, those are nutritional calories, which are equivalent to 1,000 of the little calories that we use here. So what is a calorie? A calorie is basically, little calorie is little c is the amount of energy that's required to change 1 gram of water by 1 degree Celsius. So a calorie basically is that, how much energy required to change that 1 gram of water by 1 degree Celsius. One way we use energy is to change the temperature of a substance. Heat flows from hot to cold or cold to hot. Heat transfers from hot to cold. Yeah, so the hot guy gets cooler, cool guy picks up the energy, gets hotter. They're in an insulated container. They kind of meet somewhere in the middle of their temperatures. So really, heat does flow from hot to cold. So you should know, like I said, the different units that we come across, you definitely should know that conversion. And not too much in this class, but occasionally in this class in 1A and 1B, that does pop up a lot, that relationship there. A joule is a kilogram meter squared over second squared. Very rarely do people use Newton meters. That's what that stands for, Newton meters. Too much anymore. So as I mentioned a little bit earlier, jumped the gun apparently, but thermal energy, again, is really associated with the motion of molecules. And as I mentioned, really the more molecules you have, the greater thermal energy something will have, although the temperature may be lower than something like our coffee cup example. Obviously, the less molecules, the less motion that you'll have, and the less thermal energy. All right. That was the example we just talked about. All right. So heat is the difference between basically two objects at different temperature. And as we talked about, it does flow from hot to cold. And that's the transfer of thermal energy between two bodies. Exothermic processes, as we've been talking about, are any process where heat and energy is released. So that basically is transferring it to the surroundings if it's the system. If it's the surroundings being exothermic, it would be transferring it to this the system in that case. An example, if you light a match or even a Bunsen burner, you could feel the heat coming off, right? So the system is the Bunsen burner or the flame and the combustion reaction, and it is releasing heat and energy to the surroundings, which is why you could feel hot, right? Because your hand would be picking up all that heat and energy from the flame. Endothermic processes, as we've been talking about, is any process where heat and energy is being absorbed. So for example, if you were holding onto a test tube and the test tube started to feel cold to you, that would be an endothermic process for what's happening in the test tube. Because you're holding it, it's feeling cold because all the energy is leaving your hand, going to the test tube. So your hand feels cold, right? And vice versa, if you held the test tube and it felt hot to you, the system in the test tube would be releasing all that heat and energy into your hand. And obviously you would feel hot in your hand. So that would be an exothermic process in that case. So melting ice to form liquid water, as we talked about, again, you need to put the heat in. There are a couple of sort of units that we come across in terms of heat and energy, and how we know by just looking at, for example, a particular value, if it's an exothermic or endothermic process. So there's a couple of ones that we will see. Delta H, as we'll talk about, is the enthalpy. It's basically the heat of a reaction. And if it is an exothermic process, typically your delta H value will be a negative value. So that indicates that the energy is being released. And if it is a positive value, that is usually what occurs with a endothermic process. So that's a very common unit of energy that you deal a lot with. We'll talk about in this chapter. In 1A, you deal with it a lot, and also 1B. Another one that we will deal with in this class as well is Q. Q represents the heat, our energy. And if you have a Q value that is negative, that usually means a exothermic process. And if you have a Q value that is positive, that is typically an endothermic process. So in general, any type of energy value or unit that is given to you in a problem, and if it is a negative value for that energy, it implies that overall what's happening there is going to be an exothermic process. Heat and energy is going to be released. And if you have any type of delta H, that you end up with a positive value, that means everybody's basically absorbing energy as a result of that process. Any questions on that there? All right, we will lay it up there for today.